Now we come to the session 16. So here with the method of integrations. We already know in the integrations form, so integral of a definite integral, indefinite integral. In the same way, we come to the complex integrations. So first, I give introductions. The readers is familiar with the theory of integral of a real variable. In the case of a real variable, the distinctions is made between the definite and indefinite integrals. Definite integral is regarded as a limit of the sum and indefinite integral as process of reverse of differentiation. So you know the familiar. The integration is a reverse process of a differentiation. In this case, what's a definite integral? Indefinite integral. In case of definite integral, some integral constant appear. Integral constant appear. In case of indefinite integral, the integral constant is eliminated. Means is get cancelled. So eliminated in the case same way. So with this, the method of real variable, the method of integrations, definite and indefinite integral. In the same way, you are applying here in the complex integrations. So the process we can make a similar distinctions between the definite and indefinite integral of a complex variable. A definite integral of a complex variable are usually known as a line integral. So definite integral as a line integral in case of complex variable. As in the case of a real variable, in the indefinite integral of a complex variable is a function's whose derivative equal is given analytic function in a region. See, so analytic function is a region, so bounded regions. So if we take an acquired area, so divided that x-axis and y-axis. So first we are integrated along a line and boundary like that. So if we come to the problem, we know the method of integrations in the complex cases. In indefinite integral, the indefinite integral of a many elementary functions can be obtained inversions of known derivative formulae. However, the theory of a definite integral of a real variable does not extend straightway to domain of complex variables. See, this is the difference between the real variable and the complex integrations. So, in the real variable, only two methods, definite integral and indefinite integral. Some formula we apply directly, we get the evaluations area or definite values, we get it. But in case of a complex, so definite, what's the line integrations, region of integration, path integrations, this is the way we are obtained. But here integrating what's the real part, you are converted to, suppose something is given, I want to totally convert it in terms of x or in terms of y. Then integration run from along the x-axis or integration run from along the y-axis. This is the way in a complex form. So for some examples, in case of a real variable, in the case of real variable, path of the integrations of integral of a to b f of x dx is always along the x-axis because integral with respect to x. So derivative in terms here, integration run from a to b f of x dx is always along x-axis. X run from a to b. So x is equal to a and x equal to b. Means integral run from a to b. But in the case of a complex function f of z, the path of the definite integral a to b f of z dz, see f of z dz may be along any curve joining the point z equal to a and z equal to b. Thus, generally the value of the integral depend upon the path of the integrations. So the values depend upon the path of the integrations in case of a complex function. So, however, we shall see that these variations in the value of the definite integral will disappear in some special circumstances. See, some case is disappear in the special circumstance. We shall prove that if f of z is analytic in simply connected region D. So here f of z is analytical in a simply connected region D. Then integral 1 from a to b f of z dz is independent of the path in D joining a and b. This is the independent path from the line joining a to b, but a and b lie in the domain D. So this is the then integral 1 from a to b f of z dz is independent of path in the joining a and b, where a and b are the point in D. We shall express a complex definite integral in terms of a real integral, and this will be more convenient to the reader who is familiar with the theory of a definite integral of real continuous function. See, this is the basic introducing the what's the reality in you're integrating in the real conditions. If you come to the complex conditions, what's the difference? So here in the path, see in the complex we are integrating along a path. This is independent of a path in from A to B, but the value of A and B lies in the region D. Value of A and B lies in the region D, the same way. So some basic definitions. Suppose if you take a line A to B in a closed interval. So divide this interval a number of a subinterval. Divide interval number of subintervals. Suppose I take suppose A1, A2, A3, etc. up to that. So take a small interval A to A1, A1 to A2, A2 to A3, etc. Means divide number of a subinterval. I call that number of subinterval. The same way. So I'm giving a definition. Some basic definitions. The partition. Let closed interval A comma B be a closed interval where A and B are real numbers. Divide A B into n subinterval. Divide closed interval A B into number of subinterval n subinterval. Say A is equal to T0 T1. So if we take this T1 T0 to T1, T1 to T2, T2 to T3. This is the closed interval. T1 T0 to T1. So one interval. T1 to T2 is one more interval. T2 to T3, etc. Tn minus 1 Tn. This is equal to this. So we intersect n minus 1 intermediate point T1, T2, etc. Tn minus 1. Satisfying the inequality, suddenly A less than A equal to the endpoint A equal to T0 less than T1 less than T2, etc. less than Tn minus 1 less than Tn is equal to B. So where A and B is the endpoint. Within the endpoint, dividing number of a subinterval, that interval should be equal to T0, T1, T2, etc. Tn. So then the partition P equal to set up all T1, T0, T1, T2, etc. Tn. The partition P, then the partition, the set of all T0, T1, etc. Tn is called partition of the interval, a closed interval AB. This is called the partition of the interval, closed interval AB. And greatest of the number T1 minus T2. So if you take a difference, any consecutive difference. So what's the difference? T1 minus T0 or T2 minus T1 or T3 minus T2. This is the difference. Or Tn minus Tn minus 1. This is the difference. The greatest of that number is called norm of the partition P, which is denoted by norm T norm less than or equal to absolute values of n. That is the case. So we come to the another. What's the area? What is the arc? What's the reason we are defined? See the equations. If you take a complex equations, what's the variables in case associated functions? The variable associated function. Suppose the equation z of t. Here these variable associative complex functions. Associated complex function z. Suppose z equal to z of t is equal to x of t plus I y of t. X of t plus I y of t, where t lies between the interval a less than or equal to t less than or equal to b. And x of t and y of t are continuous functions of t. So this is the function we defined. Then the function z equal to z of t equal to x of t plus I y of t, where t lies between a and b. A less than or equal to t less than or equal to b, and x of t and y of t are continuous functions of t, represent an arc L in the complex plane. Here, the parameter representations x is equal to in terms of x of t, y is equal to y of t. The parametric representations x equal to x of t, y equal to y of t is also used. An arc L is said to be differentiable if derivative of z of t is exist and is continuous. So z of t is exist and continuous. You know the basic definitions regarding the derivative functions. So what is the derivative of that? What is the limit and derivative? You already know the previous slides in the complex derivative function, complex continuous function, complex limit functions, limit of the complex number, limit of the derivative function, limit of the limit, then continuous function in the case of complex variable. Same. The regular or smooth arc. See, a regular or smooth arc. An arc L is said to be a regular or smooth arc. The derivative exists and derivative should not be zero. So, smooth or derivative z dash of t is exists and derivative z of t should not be equal to zero. That is called a smooth or regular path, a regular arc of there. Geometrically speaking, a smooth arc has at every point at a tangent whose direction is determined by the argument of a derivative of z. Argument of derivative of z means this is geometrically speaking. The smooth arc has at every point a tangent whose direction is determined by the argument of derivative of f of z. Argument of the derivative of f of z. So we come to the piecewise differentiable. Suppose if we take that closed interval a comma b. So you are dividing number of intervals 0 t0 to t1, t2 to t1 to t2, t2 to t3, t etc. These are a closed smooth curve. See, if we this differentiable at a and b, this differentiable in the sub interval t0, t1, t1, this is partition. This is continuous. This close and piecewise is also continuous. This continuous. This is continuous, and means that way. An arc L is said to be piecewise differentiable if among its various representations there exists at least one representation such that interval closed interval a b can be divided into finite number of subintervals. We divided into finite number of subintervals. Say closed interval a1. Close interval a1, a2, close interval a2, a3. So this is continuous. So we are dividing. So a1, a2, a3, etc. b. So first interval a to a1, a1 to a2, a1 to a3, a2 to a3, a3 to a4, like this. Piecewise is continuous in the interval. So say a1, a2. This is a closed interval, etc., etc. an minus 1 b, on each of which derivative of z of t exists if the addition derivative should never zero on any of this subinterval, then L is said to be a piecewise regular or smooth continuous differentiable. See, if we come to the one more simple arc, simply say Zordon arc. What is a simple arc? See, the definition is the simple arc. Now, arc L is said to be a Zordon or simple arc if z of t1 should be equal to z of t2. So, z of t1 is equal to z of t2 only where t is equal to t2. Or t1 not equal to t2. This implies z of t1 should not be equal to z of t2. This is called simple arc. So, an arc L is said to be a Zordon or simple arc if z Z of T1 should be equal to Z of T only when T equal to T2. Or if T not equal to T1 not equal to T2, then this implies Z of T1 not equal to Z of T2. The same way we explain in the closed curve, if the point of the corresponding to the value A and B coincide. So, if the point of the corresponding to the values of A and B coincide, then the arc L is said to be a closed. See, refer this. The corresponding point A and B are coincide. The point A and B are coincide, then the arc L is said to be a closed curve. If L is arc, the arc Z equal to Z of T, the T lies between A less than or equal to T less than or equal to B, the arc defined as Z equal to Z of minus T, where minus B less than or equal to T less than or equal to minus A, the value, my negative values. So we depend upon the values. Then the arc defined by Z equal to Z of minus T, then minus B less than or equal to T less than or equal to minus A is said to be opposite arc of L and is denoted by minus L or inverse of L. Minus L or inverse of L. We come to the counter. What does the mean counter? Counter is continuous chain of finite number of regular arc. So counter means the finitely continuously arc or regular arc. Finitely continuous regular arc is called a counter. A counter is a continuous chain of a finite number of regular arcs. A counter is a continuous chain of a finite number of regular arcs. A counter is said to be a close if it does not intersect itself. Is said to be a close if it does not intersect itself. And the starting point of A of the first arc coincide. The starting point of A of the first arc coincide with the end point of B of the last arc. We have read that. Again, I am reading the a counter is said to be a close if it does not intersect itself. It does not intersect itself. Close means does not intersect itself. And the starting point of A, the first arc, coincide with the end point of B of the last arc. The integral along such a closed counter C is written as integral of C f of z dz. The counter C represent a counter means continuous counter. This is integral of C f of z dz. The boundary of a triangle, circle, quadrilateral are examples of the closed counters. This is an example for counter means triangle is example, no continuously, no break. That's the circle. If you take a triangle, see this is to represent a triangle continuously, no lifting any. This is continuous. A circle, quadrilateral, that is a quadrilateral, and they are the example of